Hey guys, welcome back. So today's video, we're going to go over some setups and then we're going to get into the FEA. So we're actually going to start analyzing these designs and see what we find. So what is FEA? That's called finite element analysis. Essentially, it's a tool for mechanical engineers or whoever's doing it, but basically you can put a load on a material and it'll tell you what the stress and strain and deformation and things like that are. So it lets you essentially simulate something and find out what it's going to do before you actually build it. So it allows you to just speed up the development really quickly. You can software make something, software test it, and then if you don't like it, you can change it and retest it. So it just speeds things up. So what you're looking at here, this is a piece I modeled, and this isn't a main bearing cap. In fact, this represents the block itself that the cap goes into. So I basically just took the engine block and took some rough measurements and whipped this thing up. And this little part in software is defined as being cast iron. So it'll have the strength and rigidity of a cast iron part. And what we're going to do is we're going to bolt on in software the factory cap. And we're going to install bolts that are the same dimensions as the factory bolts. Then we're going to torque them up to the factory torque spec so that they're squeezing the cap onto the part here the way the factory would. So at this point, it's as realistic as it can be, and then we're just going to push on the cap and see how much it moves. And that'll essentially give us a baseline and say, well, a stock system performs this way. Once we know that, now we can evaluate any future designs to see if they're better and by how much. So here we go. Okay, so here's our setup. We've got the factory cap bolted onto the factory block. We have 2 bolts installed. These are torqued up to 45 foot-pounds. So I go in here, come over here to torque. This thing always jumps units on me, but anyway, if you throw this thing down in foot-pounds, you see we got 45 pounds of torque. And yeah, there's one of the, there's a cross-section view. You can kind of see the bolt. The other one's the same. So essentially those bolts are torqued up just like they would be from the factory, squeezing that stuff together. We've got our little notches on the side of the bearing that hold that up. And lastly, we have a load. Now, let me show you what we did here. This part was a little difficult to figure out. So what we did, yeah, there you go, kind of shows up. So what I did was inside the bearing itself, this is just like an artifact of the software, it's just easier to do. What I did was I put this incredibly small step in the bearing. You can see it right there. If I keep zooming in, there's a little flat spot in the top. Now in practice, that's a tiny little spot. It's only like, I forget, 40 thou wide or something. It's very small, but what we did was we put a load right here. So what we wanted to do was we want to throw a big load right in the middle of this bearing and just see how much it bends. We're going to use this data to evaluate our new design. But there's a key thing to remember when you're doing this. So when you torque these bolts, this bore is going to bend. So what you have to do is you can't look and say, well, how much did this move when I put a load on it? What you instead have to do is you have to torque the bolts and apply an extremely small load and see how much it moved. So imagine instead of putting like thousands of pounds of force, just put like 1 pound of force, something that's very, very small and really isn't going to move it much. And then you see what that number is, and that's your actual baseline, because this whole thing is going to distort just from torquing the bolts. So I could apply a load of, say, 0.001 pounds of force, and you'll still see deflection, and that deflection isn't from load, it's from torquing the bolts. Now in practice, they're going to torque the bolts and then line bore and line hone. So this will be a perfect circle. But for the purposes of our analysis, we torque the bolts and we apply a very, very small load and we write down how much deflection there is. And that's considered the 0. Then we'll apply the load we actually care about and we'll subtract the difference in movement. So say it moved 1 thou when you torqued it and it moves 2 thou when you applied the load. Well, the difference would be 1 thou. That's how much it moved under load. All right, so with that concept in mind, let me show you how this bearing performed. Okay, so this is the results of putting 4,000 pounds of force on the bearing. So we already did the one where we put 1 pound of force and we just wrote down how it performed. And then we did this one at 4,000 pounds and we saw how it performed. So let me show you, let me explain this a little bit. All right, so you might see the colors. There's actually a scale to this. So if you come over here, basically the dark colors are where it really didn't move. And as you go up the scale, you'll see at the very top we moved 0.0027, so almost 3 thousandths. And then it changes as you go through the colors. And this is showing displacement. So this is how much it actually moved. So for this setup, this bottom is fixed. See the little lock? So essentially the software treats that like it's glued to something rigid. And then you can evaluate how much all this stuff moves. So you can see as the colors change where things moved. So curiously enough, if we zoom into the center of the bearing, see how it goes from this bluish color to like a bright green? Well, if you look at our scale, that blue going into green is increasing in movement. So you can tell that that big green spot is it lighting up with movement. Which, you know, it's not really surprising. I knew the factory one, because it has all these notches and thin geometry up here, we kind of knew that was going to move some. But it shows up in software. And you also note there's like a cold spot to the left and right. Why is that? Well, that's because it's thicker right there. See? So right there you've got that big cut where it's thin, it lights up, but you notice where it's thicker, doesn't move as much. Keep that in mind for later. Okay, so let me show you the actual numbers on paper of how much this thing actually moved relative to its origin. Okay, so here's our results for the Mazda. We're going to show you the other stuff in a second because we already did it. But here's how the Mazda bearing performed. So we put 1 pound of force on the bearing, and we noted that that spot moved this amount, 7.1 times 10 to the negative 4. So what that means is that's basically in inches, 0.0007157 inches. And this one's about the same. We did 2 different points. Let me show you those. So these are the 2 points. So right where we were touching, I put a little dot right here, and then so that's basically in the dead center of the bearing, and then we did one up here towards the top as well. I didn't know if this would change much, but I figured I should check. So that's the 2 points. That's when you see these 2 numbers, that's what you're looking at, is the stress in those 2 points, or the displacement in this case. Okay, so after showing you those numbers, this is essentially like 0.0007. This is 0.0007. And when we come down here, when we put 4,000 pounds of force, you see these actually moved a lot more. So we got 0.0013 and 0.0015. So how much did they actually move when you do one subtracted from the other? Here's the results. About 6 10,000ths, and if you round that up, that's about 8 10,000ths. So if you took the average of this, it would be, what, a little over 7 10,000ths? Something like that. So it moved about 7.2 10,000ths. Something like that. So it's less than 1,000th. That's also with 4,000 pounds of force. That probably doesn't seem too bad. Less than 1,000. But then again, think about bearing clearances. I mean, that stuff is, you know, down to like the 10,000th. So that is a good amount of movement. Also, you know, what if the loads are higher? So now we're going to look at the new design. Okay, actually, before we look at the new design, let me give you guys a primer on why we're doing this new design and why we're doing the numbers like this now. So let's say we wanted to build new main bearing caps, and the assumption is that we can build them that are better than the originals, right? Well, how do you know that? So if I was to go build a bearing cap that I think is like a balance of cost and ease of manufacturing and, you know, things like that, and I think it'll be better, but it's also trying to keep it cheap, keep it simple, whatever. So say I go and build that, and then I test it, and it's only like marginally better than what I've already got, then I may have to go back and build a better one. And then eventually I may discover that no matter what I do, I really can't make it much better. So what you want to do is you want to take things to their like extremes to see if there's actually a case for making it better. So what we did, the design that I showed, is essentially that's about all I can get. I don't know much else to do to make a bearing that would be stronger than that wouldn't be a lot more difficult to do. So the goal is we're going to evaluate that design, and what I expect is that you see these numbers here, I expect that our new design is going to be significantly better than this. And then, you know, based on those numbers, well, I already know what they are, but based on those numbers, then we might decide, hey, maybe we want to build some lesser cap. Maybe we can build something that's still really good. So maybe we can build something that's still really good, but it's also easier and cheaper to make. So with that said, here we go. All right, so here's that original cap. We're going to flip back and forth between the 2 designs, and I'll let you guys see the difference. So this is the factory cap. Now we're going to go to the new one. That's the new design. Notice any differences? Obviously the shape's different, but you notice the colors are different. Watch me flip back and forth. So in this one, we see that there's a green spot that kind of lights up green, and there's a couple of blue spots here. And look what happens when we flip back to the new one. See, these blue spots are much more pronounced. They're a lot larger, and you see they're really stretching through the whole design. And that green spot in the middle is gone. Now it's just like a like a pretty blue color. So what does that mean? Well, if you remember the scale down here, when you go from green to blue, it just means it's moving less. So that's good. So without even telling you the numbers, there's a good chance that this bearing is performing better just by looking at the colors. All right, so now let's get into the numbers. Okay, so here's the new design. So we started off with these 5 times 10 to the negative 4, so that's like half a thou. I think that's similar to, yeah, we had like 7s over there. So this design, it flexed under torquing the bolts, but it didn't flex as much. Yeah, this one flexed a little over 7/10 when it was torqued. This one only flexed 5/10. Now that's interesting to think about, that this bearing cap flexes less when it's torqued, because it's actually torqued higher. The cap on the factory one I had torqued to 45. This cap I had torqued to 60 foot-pounds. So that is interesting that despite torquing it higher, like 33% higher, despite that, it's still, it still moved less. That's a testament to the design and the materials and whatnot. And here's the numbers after we torqued it, and then we put our load on it. So these are just torqued without load. These are torqued with load. Do you notice anything? Wait for it. Do you notice anything? Okay. These are all almost the same. Look at this number here. 5.05 e to the negative 4. That's 4.44 e to the negative 4. That didn't change much. If you look at this one, 5.03 to 5.04. I mean, this hardly changed at all. And so I did the math down here. This is how much they moved. So this one moved 0.000. Now we go to the tenths. That's also a 0. Now we go to the hundredths. It moved 6/100ths of a thousandth. That's insane. That's an order of magnitude stiffer than the other one. So if you remember, we'll come over here. This one moved 0.006. And this is 0.000. I think I said that wrong. That's 4 zeros before the 6. That's 3 zeros before the 6. So this is literally 10 times more rigid according to this point. And if you go to this one, I mean, this is just insane. There's literally 5 zeros before it moved. So that essentially shows it didn't move. But even if you took the worst case of the 2 points, that's still 10 times more rigid than this design. And if you were to like take the average of these two and the average of these two, I mean, it's even better. So no matter how you look at this, even the worst interpretation of this data is this design is about 10 times more rigid. And that is just awesome. So it's kind of hard to believe, but apparently there is a ton of room for improvement to stiffen up the bottom end of this motor. And this is without using a girdle. This is very telling. Now, it's possible that I've made a mistake on this numbers through the FEA or something, but if this is true, that we're really moving not even 1/10,000th of an inch, whereas we were moving 10 times that amount, then we don't need a girdle. It's not necessary. What we need is just a badass cap with some really good fasteners. Pretty telling. This is not intuitive until you really work it out. I would not have thought this. I would have always thought you need a girdle too. So, pretty interesting result. Well guys, this is why you do engineering. You can find some cool results doing a little math and simulation and discover things that weren't really immediately obvious. So I would have never guessed. I think I did a video that when you're watching this, I would have posted yesterday, where I said that this would probably be double to triple the stiffness. I wouldn't have thought it would have been 10 times stiffer. There was part of me that thought maybe that would happen, but it kind of also seemed like the optimist and that something else would prevent that. But it turns out that's not the case. It turns out you just make this thing 1.25 inches thick, solid steel, and don't have it neck down anywhere, and bulge on the sides to really spread that bolt stress out so it doesn't just shoot over here. Turns out you do all that, it really is 10 times stiffer. So how about that? So now I've got a pretty good reason to build these. I know now that I can build a cap that is significantly stronger and very significantly stiffer than the existing one, even if it drops right in and bolts right up. Well, with different bolts. But anyway, it still bolts up to the block and crank and all that. So pretty awesome news. And I love doing stuff like this to kind of see, I now have a better understanding of why these bearings wear out. When I swap back to, this is the Mazda one we're looking at. I mean, it's obvious that, this bearing is just bending. You know, I did this simulation with 4,000 pounds pushing on it, but I really don't know what the numbers are. But I mean, the thing is, if you guys remember that equation, force equals 1/2 mass velocity squared. So the v squared is what gets you. You know, the loads in these bearings might not be so bad at 7,000, but you go to 8,000, 9,000, 9,300, 9,500. As they start creeping up, the loads are going up with the square due to the velocity being v squared. So apparently that's what's been killing these things. You know, it's just too much load, and it gets to the bearings and pushes on them too hard and causes these, you know, stuff starts bending and flexing, and you get all these weird wear patterns. So I think we're onto something. Looks like we've got some definite room for improvement. At this point, I definitely feel comfortable getting rid of that main bearing support plate. I think the real problem, you know, I'm not even going to bother, but you could try to like bolt a piece of sheet metal to this, but you can tell that it's, you know, no matter what you do there, think about this. If this piece of metal that's 0.6 inches thick, if that's bending, there's no piece of sheet metal you're going to attach to this that's going to stop that by any significant amount. So at this point, I feel confident that, you know, we're going to delete the main bearing support plate. We're going to build some massive honking little main bearing caps, and we're going to go with that. So hope y'all enjoyed this video. I know it's been kind of we've never done FEA analysis, or actually I've never designed a main bearing cap until today. But this was fun, and now you guys hope you like it, because we're about to build these. And if there's any interest, we'll document it along the way. All right, you guys take it easy.